You're all madly scrambling to write down that definition. That's good, but I'm going to start talking. So you saw limits a little bit in advanced functions, I know, and we use the notation for limits, but it turns out there's more to them than just sticking it in front of the stuff we were doing during the rates unit. What we were doing was finding slopes of tangents and rates of change, right? Instantaneous rates of change. But there's more to limits, and that's what we're going to explore in the first unit of this course, is really a bit more on what the definition of a limit is. We're still only using it for like one thing, which is calculus. Calculus is based on sort of some of the stuff related to this. And it's still going to have a lot to do with slopes of tangents, be related to that at least. Okay? But there are more to limits. They are used in other areas. You don't need to know this, but it's just kind of interesting, I think, that they are used in other areas to do limits of infinite sums and different things like that. So if you were to take mathematics beyond high school, you would see limits a lot in all kinds of places, definitely in calculus. Okay, but there is more to them. And so what's going to happen today is that at first it's going to seem weird and you're going to kind of not know where it's going. But after we do a bunch of examples, you're going to start to get a bigger picture of exactly what's happening, hopefully. You'll see from the diagram here and from the stuff we talk about why we talked about piecewise functions on Tuesday, the previous day, is because they're a great way of exploring the true nature of how limits work. Okay, but we do them about all functions, and you'll see that as well today. But it's going to seem like a simple idea, but I'm telling you, sometimes the simplest ideas have like the biggest ramifications, the biggest profound impacts on its knowledge. So yes, it's simple, but we're going to spend a long time talking about it because it's so important, and because in some ways the nuances and the finer details actually mean it's maybe not as simple as at first glance. So I would just encourage you to think about this and really visualize. We're going to do some different demos to help visualize and understand what's happening. So the definition goes, the limit of a function at x equals a is the y value it approaches as x approaches a. Okay, and this is what we're going to explore over the next 10 minutes or so. Now, a heads up, a function may have a limit at any particular value, or it may not. It may have a limit at all values. It may have a limit at only some values. If it had limits at no values, I don't think it would be a function, so that probably would never happen. But like limits, the functions don't have limits everywhere. Sometimes they don't have one, okay? And sometimes they do, and that's kind of what we're exploring. So you should have this diagram in front of you, but I'm going to use a little applet here to help visualize what's happening. Before we get started, what does this notation mean? This is saying the limit as x approaches -6. What does this mean? What's that negative doing there? From the left, correct. And this plus sign here means from the right. So this one is saying the limit as x approaches -6 from the left of f at x, what does it equal? So once you get that written down, I want you to look up here. Now take a look at where -6 is. It's that red dot. I'm going to zoom in here a little bit. See that red dot? That's what we're approaching. So I'm going to approach it from the left. And this is me approaching, the x value is approaching -6. And you're going to have this epiphany of what's happening here when you see what y value it's approaching. Ready for this? It's going to be pretty intense. Can you see what y value it's approaching? Anybody confident enough to hazard a guess? It's not more complex than your intuition says right now, I think. 4. That's exactly right. Very good. Well done. The limit as x approaches negative 6 from the left of f at x does equal 4. Now let's go from the right. So again, we're approaching negative 6, but now we're approaching it from the right. You want to watch? What's it approaching? 4. You're like, sir, this is really simple. What the heck are you even talking about? That's true. That's really easy. So what does this one say? The limit as x approaches negative 6 of f at x, not from the left, not from the right, just like the limit as x approaches negative 6 overall. What do you think it might be? 4. Very good guess. And right now I'm going to leave it at that. We're going to come back to it in a minute because we're going to do a few more of these, and then we're going to have something to really think about. Now we're looking at the limit as x approaches negative 2 from the left and from the right, and then negative 2 overall. So let's take a look at from the left first. So here we are over here at negative 2, and I'm going to approach it from the left. So watch that purple triangle approaching from the left. Okay, very nice. What y value is the function approaching, or that triangle approaching, as we approach negative 2 from the left? It's approaching 1. Good. Now we're going to approach from the right. Watch. Now what value is it approaching? Somebody else? Yeah. 3. So here's my question to you. What do you think the overall limit is? The limit as x approaches negative 2. Does anybody have a guess? Okay, we got 1. Anybody else want to guess? 2 people who are willing to guess. Abdullah's hand is half up. Daniel's up. Did some of you peek at the lesson already and you know what's coming? Okay, good. Emery, what do you think?
So do we like find the average?
Good guess. I expected somebody to have that. We could find the average. That's possible. Turns out that's not correct, but that may have been useful. I don't know. Anybody else want to guess? Why do you say 1?
Because 1 is where the graph actually exists.
Okay, so if we go back and we think about the notation of piecewise functions from the last day, and if you weren't here, you know, the colored in circle means it equals 1 at negative 2, and the empty circle, or we call this an open circle and this a closed circle. So the open circle means the function doesn't equal negative 2 at that point. It doesn't equal 3 at negative 2. And if it did, if it was colored in both, then it wouldn't be a function, right? So it's important that at that point, only one of those is a closed circle. That's another good guess. Turns out that's not quite right. I figured somebody would want to say that, though. Same thing last period. Anybody else have another guess? Out of guesses. Why 2? Just because, oh, it's in between. That's kind of what Emery said. Yeah. No, it turns out that's not quite correct. So it turns out it does not exist. And all of a sudden, and we say D, N, E. And all of a sudden, we start to realize there's more to this than the simple idea of your evaluating the function at that point. Turns out there's an important definition, we're going to write it down in a moment, about limits. Okay? And I'm going to show you what. What is this? F at negative 2. This has nothing to do with limits. This is just evaluating the function at negative 2. And that's what, was it Daniel that said that? It's equal to 1, right? Because it has the closed circle there. So look what happened here. As I approach from the left, I approach 1. As I approach from the right, I approach 3. At negative 2, it's 1. But that turns out has nothing to do with the limit. in this case, the limit does not exist. Why? Because I'm going to go back to -6. The limit as it approaches from the left and from the right has to be the same for the limit to exist. And in this case, they were both 4, because from the left and the right, it's approaching 4. So the limit exists, and it is the value that it's approaching from both sides. Naturally, that makes sense. Whereas in this case, it's approaching something from the left and something from the right, but those things are different. And that's a key aspect of limits, that they have to be approaching the same value. It has nothing to do with the value of the function at that point. Interesting. We're going to see that in a moment. Okay, so we're going to write down this formal definition here. Okay, so the limit as x approaches a, you can't just say, by the way, don't write this down, limit as x approaches a equals. That's like saying multiplication equals. Okay, that's meaningless. It always, and be careful because this happens, it has to be of something, the limit of something. So we're just talking about a function. Equals L. Does anybody know how to spell if? I always forget. How do you spell if? I'm just kidding. Does anybody know what that word actually means? IFF? It has a definition in mathematics and logic. No? It means if and only if. I'm going to write that down off to the side somewhere, or maybe down here so it's out of the way of our nice definition. IFF means if and only if. So if one thing's true, the next thing is true. If one thing isn't true, the next thing doesn't true. This is, we're not going to get into this too much, but turns out there's this whole thing of like logic that you can explore, and if and only if has a very specific meaning in that kind of logic. Okay, so the limit as x approaches a of f at x equals L. L is the standard that we use in limits to mean some value, capital L. So don't choose a different letter, make sure it's L. If and only if the limit as x approaches a from the left of f at x equals L, which equals the limit as x approaches a from the right of f at x. Important definition. If you were ever asked to give the formal definition of a limit, that's what it would look like. A little bit more notation. There's a lot of like new notation, new ideas, new definitions that are particular definitions that we're doing today. So there's a lot to it. We call this the left hand limit. We shorten it to LHL. So if you're approaching from the left, we call that the left hand limit. And in this one, we call it the right hand limit. Or RHL. Okay. Any questions about that? Yep.
So like the second equation, so that's just the LHL?
Yeah. So I'm just going to go back and make a couple little notes here. Remember when we looked at these first three, A, B, C? So the limit as x approaches -6 of f at x equals 4 because the left hand limit equals the right hand limit. Right? So remember you guessed, and it was an intuitive guess. I can't remember who guessed, but, and probably a lot of you are like, well, It's probably 4. Like, sir, this is really easy, and I don't understand why we're even talking about this. It seems like grade 9 stuff or something. But turns out there's more to it. Turns out there was a reason why it equaled 4, because in this case, it did not exist. And again, that was because the left hand limit does not equal the right hand limit. And that's the definition of a limit. We didn't talk about any of this in advanced functions. We just used that notation. We talked about this idea of not equaling a value, but approaching a value. We talked about that a lot because we talked about that in terms of behavior around asymptotes and such as well. And it turns out this is a really powerful concept. And one of the reasons why is because sometimes I can't evaluate a function at a point. But if I can evaluate as it approaches that point and see what's happening, that can still be useful. And we saw that with instantaneous rates of change in the last unit. Okay, stop me if there's any questions. We're going to move on and look at a couple of different cases. You notice why, I hope, as we continue to explore these next few cases, why we looked at piecewise functions yesterday or on a couple days ago, because they're a great picture of exploring all the different nuances and properties of limits in graphs. But what we're going to explore over the next few days is different kinds of graphs and how you would calculate limits for all kinds of functions. For a piecewise function, that's what we're exploring right now. We're going to look at others as well. So this one says the limit as x approaches 1 from the left, as x approaches 1 from the right, and as x approaches 1 overall. And then it asks us to evaluate f at 1. And if you look at 1, you can see what's happening. So you can start to guess what's going to happen. Uh-oh, what's going on here? There we go. So I'm going to go up to 1. And so there's 1. And watch what's happening as I approach from the left and as I approach from the right. What is happening? Who can describe what's happening to help us answer all of these questions? In terms of limits, what do you think is happening? What value is it approaching from the left? What value is it approaching from the right? 6. So, what do you think? Now, what does this little dot mean?
That's where the graph exists.
That's where the function actually exists there. In fact, and I'll give you a chance to write this down later, here's the equation of this function. It's got a whole bunch of parts to it. You don't have to write it down, but if you want to, you can. Okay? And look at this. As I approach 1 from the left, so less than 1, when x is less than 1, I'm using this quadratic, which is this thing right here. And as I'm bigger than 1, when x is greater than 1, I'm using this quadratic. Look, it opens downwards. It's this one right here, see? But at 1, the function equals 4. I don't know why. This is just made up silly thing. Like, I don't know when this would ever actually happen in real life. That's not the point. The point is it nicely illustrates limits. Okay? So at 1, there's the function there. And so some people think, isn't it approaching 4? Because at 1, it's going to be 4. I know that. Some people might have, if you notice that, you might have thought, well, it's approaching 4 because that's what it's going to be when it gets there. And that is not what we mean by approaching. It has nothing to do with its value at that point. It's what is it approaching. And this is the visual that demonstrates that. It's approaching 6. So from the left, it's approaching 6. From the right, it's approaching 6. If the left-hand limit equals the right-hand limit, then the limit is that value. But curiously, at that point, the function actually has a different value entirely. We call this a pop-out. I don't know if that's a formal term, but that's what we call it. When, like, just for a point, the function pops out, equals something else, and then kind of goes back to whatever it was doing before or whatever. Okay, and that is something that can happen in real life. Like that's a possibility. So again, that's like a nuance of limits. Don't be fooled that the value of the function at that point actually doesn't have anything to do with it. It's just what it's approaching from the left and from the right. So the last 4 that we're going to do here is that positive 4 from the left, positive 4 from the right, 4, the limit as x approaches 4 of f at x, and f at 4. I'm going to go back to our diagram here, and you'll notice what's happening. So here's 4. Okay. What value is it approaching from the left and from the right? 9, very good. Okay, we follow it over and we say it's approaching from 9. But look, if you scan, there is no point, there's no pop out. What do we call this? You already know what this is called. A hole, thank you. This is just a hole in the function. It's not an asymptote because it's not going to infinity or negative infinity. It's a hole, so no pop out. And it's the same kind of idea though. What do we say, 9? So as it approaches from the left, it's 9. As it approaches from the right, it's 9. So the limit overall is 9. But f at 4 has no value. So we're going to say does not exist. That's something we generally use for reserved for limits. But in this case, it's fine to say that about the function as well. Where is anybody familiar? Have you heard that before? Does not exist. The limit does not exist. Yeah? Why are you smiling? What's it from? Yeah, it's from that movie from 10, 15 years ago or something like that, when she wins the competition for her team and she's a hero, saves the day. Good Disney flick. Anyway, and she was talking about limits. And actually, you track that movie down because by the end of this course, we will, I believe, have talked about the limit that she's talking about. You'll understand what she's talking about. I don't even, if I recall, I don't even think it's all that difficult one. I think it's pretty easy. I feel like it has something to do with the logarithms unit when we get there, but maybe I'm remembering it wrong. Anyway, any questions about any of that? Okay, if you want to write down that function, you can, or this will be posted online. You can write it down later if you want to look at it. It's just interesting to see that this is the notation we use, and piecewise functions can have lots of parts. Would they in real life? I don't know, but you know they can. So the idea behind limits is what's it approaching from the left and what's it approaching from the right, and is it the same? Now you're going to notice that it has a very close relationship to this idea of continuity. We talked about continuity last day. And continuity is where a graph had like gaps in it or breaks in it or something like that. And we just did a visual inspection. Now we're going to talk about continuity a little bit more formally today, and we're going to do a little bit of work with it, but it's not for a few days that we're really going to get into what a formal proof of continuity looks like. So I have a question for you. Where is the graph above discontinuous? There's our graph. You've got it in front of you. Somebody just give me one of the values where it's not continuous. And remember, when we're talking about locations on functions, we're almost always talking about x values. So we would describe it as what values of x. X is our input. So what's the value of x? I can't say where y equals 5 because y is 5 in a bunch of different places as well. So that's another reason why we often talk about domain. Do you want to give me one? So at -4, it's discontinuous. Very good. Correct. Are there any others? -2. What else? At -3, it looks to me like it's continuous. There's -3. I think it's continuous there. What else? Positive 4, yep, that's where there's a hole. And the last one is 1. So also at 1 and positive 4. So this is an important idea visually. Where is the graph not continuous, discontinuous? Here because there's a jump from one place to the other. Here because there's a jump or a break in the graph. Here because there's a pop out. So this function exists everywhere, leading up to 1 and after 1 and at 1, but it's not continuous. And same thing here, not continuous because there's a hole. The function doesn't even exist at that point. I believe the function exists everywhere else because at negative 4 it does exist. At negative 2 it does exist. But everywhere else it does not exist. Or it does exist. It's just that one place when x equals 4 where it doesn't. So now I want to talk about this, the condition for continuity, or I'm spelling this wrong, continuity condition. I'm going to write this down formally, but you got to make sure you understand what it means. And this is why, like, the idea of a particular part of a graph or any part of a graph, whether or not it's continuous, we can come up with a very simple, succinct definition that involves limits. Okay, so the condition for continuity is if the limit as x approaches a of f at x, and remember, for that to be true, the left-hand limit has to equal the right-hand limit. That's all summed up in this part of that statement. Does that make sense? Equals some value, so the limit has to exist and it has to be a value. And that has to equal, anybody want to guess? Once you see it, I think it'll be obvious. Thing? Very nice. F at A. Like it. It has to equal the value of the function at A, right? That's what plugs that hole. If the limit, in this case, up here, the limit as x approaches from the left and the right was 6, but the function equaled 4, so they don't equal each other. So in all the other parts that we were exploring, if the limit equals some value L, that equals the same as the function at A. Okay, so this is the condition for continuity at x equals A. And a graph can be continuous for all values of A, all values of A in some particular domain, in the domain of all real numbers. Like, you could start to explore the continuity of functions sort of in this manner, which is one of the things we're going to do. This only handles one position. Any questions? We're going to kind of jump to something else that, again, might seem strange, but over the next few days it'll make more sense why we're doing it. And then we're going to come back to continuity a little bit, and then we're going to do one other little activity. Any questions about limits? Starting to get the picture, right? Seemed weird at first when it's like, what the heck is Mr. Bullitt talking about? Now you're like, okay, now I get it. Now I get that you're thinking about the function approaching from the left and from the right, and what value is it approaching, and that it's important that all these different little details. All right, so here is our next example that we're going to cover. Evaluate each of the following limits and illustrate with a sketch. The limit as x approaches 3 of x squared. That's the function. Putting brackets around it sometimes is useful just for clarity, but it depends on your handwriting or what exactly you're writing. But Just so you know, you're welcome to do that for your own purposes. Sometimes we will do that because it's sort of required. So remember, we were just doing the limit as x approaches all different kinds of things of f at x, where f at x was that piecewise function. That was a bit of a mess. What if I'm doing the limit as x approaches 3 of just a regular function like the simple y equals x squared, or f at x equals x squared? So it's pretty easy. I'm going to start with a diagram for this one, just so that we can use that visual to understand what this is asking us and why the way we're going to solve this is fine.
Since we know all these functions are continuous, can we just put the values back?
Well, that's where we're going with this. Yeah, we'll get there in a second. You're ahead of us. You're jumping our gun here. But yeah, very good. Okay, so what does x squared look like? It looks like this. No transformations, got a vertex there at 0, 0. I'm going to zoom in a little bit. I hope everybody's okay. So at 3, I go up and I find the function. There it is. And this is the key. As I approach from the left and as I approach from the right, isn't it approaching the same value? And we know that because of what Emery said. It's a continuous function. Like, we know a lot about this function, y equals x squared. We can visualize it. We can picture it. We know what it's going to approach from the left and from the right. So in this case, you're exactly right. Whoops. I can just do 3 squared. I just sub in and solve. Is that right? 9? Yeah. Okay, good. So it approaches 9. We know that. So what about for this one? What can I do? It's easy again. Yep, I can just sub in. Do you agree? Negative 10 sounds right? What kind of function is negative 2x? So you got to be able to identify the type of function you're talking about so you know what you're looking at, Sima. It's just a linear function. That's exactly right. So let's go ahead and do a little sketch of this one. And it's going to go like this. It's got a negative slope, so it's technically sloping that direction. And this one was at 5. I go down, and I found that the graph is at negative 10. And again, I can visualize the same thing. This is my point, is don't take for granted what a limit's really talking about. As I approach from the left and as I approach from the right. So I can, listen to this. I can sub in and figure out what the function equals at that point because I know that it's approaching that point from both sides because I know the type of function that it is. You couldn't do this with the piecewise function. You couldn't just sub in and determine, like we are doing here, what the function equals at that point because we didn't know if it would be the same from the left and the right. But in this case, we can just sub in. And what's interesting is over the next couple of days, we're going to look at some more complex limits and how to calculate them. And it's going to get harder. And you're going to forget that you can always actually just sub in. And if that works, good. You're fine. If you can't sub in, if it gives you something weird, that's where you have to explore further and use other techniques. That's what we'll talk about starting tomorrow. What in the world is going on in this one? Who can describe what's happening in this one? The limit as x approaches 2 of 10. Bradley. It's not x equals 10. What is it? You're on the right track though. Remember what we were doing before was the limit as x approaches 2 of f at x. So f at x equals 10, which means what? Thank you. Y equals 10. So now you can visualize what this function is. Does anybody want to guess what the answer is? Nobody wants to be wrong. It's 10. Very good. It's just 10. It's like if I sub any value of x into this, I'm always going to get 10. And what does this graph look like? It's a horizontal line. Y equals 10. Goes through the value 10. And so at 2, it equals 10. There's your sketch. Because as I'm approaching from the left and as I'm approaching from the right, I'm approaching 10 because it's just always 10. Sometimes those simplest ones are the trickiest. The limit as x approaches 2 of 5 over x minus 2. Let's try evaluating this. And if you're predicting and you're thinking, you already know what's going to happen and you're already hopefully thinking ahead. What happened here? 5 over 0, that's just 0, right? No, that's not 0. My goodness, don't ever do that. Yes, thank you. There's an asymptote. This has no value here. Oh my gosh, 5 divided by 0 is not 0, folks. Don't make that mistake. Okay. Uh-oh. Sorry, sometimes we do make that mistake. 0 over 5 is 0. Sure, that's fine. 5 over 0. No. This is an asymptote. Thank you. We know a lot about it. Let's draw this and see what happens. Now, I want you to think about this. If I evaluated the limit at any other point, would that work? Yeah, it would. Think about what this function looks like. I'm not going to draw the whole function. Well, maybe I'll draw it and then erase it. But so this has an asymptote at x equals 2. And it turns out as it's approaching from the right, it's going up. And as it's approaching from the left, it's going down. We could do testing around the asymptote that we did in the last course, but it looks like this, right? That's what that would look like. You actually know that from grade 11. So this one does not exist. Not because the function has no value at that point, but because the limit's not resolving to something. It's not approaching the same thing. Okay? That's why. But at any other point on this function, the limit would be fine. It would just be the value of the function at that point. Does that make sense? Then you say, some of you are maybe wondering, is anybody wondering, what if they both approached positive infinity? Is anybody thinking that? No? Yeah? What if they both approached negative infinity? Okay, so that might be a useful thing to know, but that's still a limit that does not exist because if you recall, it has to equal capital L, which is a value. Infinity is not a value. Infinity is a description of something that's happening or a concept, right? It's going to infinity. We're saying it's getting bigger forever. So just because it's approaching from the left and the right and both going to positive infinity, still the limit does not exist. So limits never exist at asymptotes. Easy enough. Stop me if there's questions. We're going to keep going. Here we're coming back to continuity. I don't know why we sort of jumped around. Maybe I should reorganize that. But anyway. So we're going to take a look at the function below. For some reason, it's missing the brace bracket. And again, we'll see how limits and continuity have a very important close relationship. Okay, so I hope you have this written down. What's interesting about this, does anybody know what's interesting about this? Some of you are like, sir, nothing's interesting about this. I don't care about any of this. Well, you took this course, so. What do you think? Oh, possibly. Possibly. If you've already done some of the math, you may know more than the rest of us do. Yep. I think what's interesting is it's asking us the limit as x approaches 1, and like that's where something's happening, whether it's pop out or whatever else. Something's going on at 1. Nothing very interesting is happening with this graph anywhere else. And that's what it wants us to do a test on. Well, it turns out that's the kind of thing we tend to do, is we look for places where something fishy might be happening, and we test around those areas. And we know that a piecewise function can do all kinds of different things. From both sides, it might approach the same thing. It might have a pop-out, so it exists at that point, but it's approaching somewhere else. It might have a hole. It might have a break like here, where on one side it's approaching something else, and on the other side it's approaching something else, and one of those sides equals that value. Like all different kinds of things can happen in piecewise functions like we're looking at here. So this is how we do the test. We're going to start with the left-hand limit. We're going to revisit this even more formally later, but this is going to look a lot like what we're going to do later. So start getting used to the way this looks. So to test the left-hand limit, this is the limit, whoops, as x approaches 1, because that's what we're asked to do, from the left of f at x. As I'm approaching 1 from the left, what does this function f at x, which is the whole piecewise function, what part does it look like? The first part, right? Because this is for x less than 1, which is to the left of 1. So it'll look like this as it approaches 1 from the left. So this is equal to the limit as x approaches 1 from the left of 4 minus x squared. And again, we know a lot about this function. It's just a parabola that opens downwards, has a shift up 4. So I could just sub in 1 squared is 1, 4 minus 1 is 3. Tell me if I'm wrong. We good with that? Right-hand limit is the limit as x approaches 1 from the right of f at x, which equals the limit as x approaches 1 from the right of, now if I'm approaching from the right, which part am I using? The last one, because this is where x is greater than 1. So this is 4 minus x. And again, that's just a line. So we can just sub in, no problems there. So this is 4 minus 1, which is 3. Folks, there's something important that's happening here that I don't want to skip over. I know what this function is like. So I know that as it's approaching 1 from the left, it's going to approach whatever value that parabola is at that point, because I'm visualizing that. We're going to graph it in a minute. Okay? So we can sub in when it's appropriate. And I know it's appropriate because I know a lot about this function. And usually that's what would happen in a case like this. So what can I conclude now? What do I stop and conclude? Daniel. Very nice. The limit. So remember, this is what it said. Find the limit as x approaches 1. Since the left-hand limit equals the right-hand limit, the limit as x approaches 1 overall of f at x equals 3. Second question, is it continuous? Henry? No, because it indeed does have a pop-out. Okay? It is not continuous because, and we're not just going to say pop-out. Like you could write that in your notes as a good note to yourself. But because the limit as x approaches 1 of f at x equals 3, which does not equal f at 1. F at 1 equals 5. Are we okay there? I'm going to quickly draw this. I know you're all madly scrambling to keep up. We got time, so. So this is, as I said, this first part is a parabola that opens downwards and has a shift up 4, so it looks something like this. Whoops, kind of missed. Okay. And this is a line that slopes down to the right because it's got a -1 for a slope. Ooh, that was a terrible line. Something like that. And at that point, it equals 5. So this is 1, this is 3, this is 5. Oh, that should be up higher. Just because of, maybe that was going to happen. Because this is actually 4 here, right? That part, I'm not as worried about. Any questions about that? Okay, last thing we're going to do, I'm going to get you to try this on your own, and then we'll take it up. And that is to sketch a graph with the following conditions. If you're ever asked to sketch a graph with certain conditions, what happens in the rest of the graph, we don't know. So you make it up. There may be other things happening, there may not. Usually we kind of keep the graph more or less as simple as possible for the rest of it. Don't start adding random asymptotes and all kinds of crazy stuff. But if you did it, it wouldn't really technically be wrong. It'll just kind of complicate things. Okay, so I want you to give this a shot. It's interesting how some people, maybe just very visual or just for whatever reason it clicks and they kind of dive right in, and other people are like, I don't even know where to start with this process. And that's fair. Think about what it's telling you. Think about the information, what it's telling you. can describe what's happening here? No, it doesn't have to be with specifics, just generally speaking, sort of what's happening. Go ahead, Emery.
So as it approaches from right side, it approaches to positive 3. So as it approaches from the left side, no, the opposite.
Yep, good. That's okay. Yep.
Okay, so when it approaches from left side, it's positive 3. When it approaches from right side, it's negative 3, and it's added to it's 1. Negative minus 1.
So something like that. As it's approaching from the left, it's approaching 3, but it doesn't equal 3. We show that with the open circle. As it approaches from the right, so it's interesting. Some people get confused because they're like, but sir, that arrow's pointing that way. But we're thinking approaching from the right. Doesn't matter which way the arrow is pointing. The arrow just is telling about end behavior. Sometimes that's enough to confuse our brains, right? As I'm approaching from the right, I'm approaching negative 3. As I'm approaching from the left, I'm approaching 3. But at 2, it's equal to negative 1, so it's got, again, like this pop out and a break. And the fact that this one looks like it might be cubic, and this one looks like it's probably linear, irrelevant. I just drew it that way because because I'm so creative, right? But you could have done a sine curve or 2 straight lines or whatever you want. This is what I mean by, like, you know, don't start adding other asymptotes and other holes and stuff in the graph, because I think that'll just complicate it. But technically, whatever you did with the rest of the graph would be fine. Don't do this. Ooh, like, oh, jeez. It's not a function anymore. Okay, any questions about that? So I'm going to give you 2 more of these. Somebody reminded me this morning, so I know that you're going to frantically try to copy them down. I will try to put them up on, they will go up in the classroom, so you don't have to get them all written down if you don't want. They'll be in the classroom with the note. Somebody reminded me this morning that they may not know this notation. This is interval notation. We start using it in calculus. I used it a little bit in advanced functions, but not everybody does. So what does it mean? This means from 2 to infinity, positive infinity. So that means x greater than 2. The round bracket means you're not including the point. From negative infinity to positive 2 means x less than 2. That's what that notation means. It's not an ordered pair. It's called interval notation. We use it when we're talking about intervals of things. We're going to do a lot of that, so you're going to start getting more used to using this. As a side note, if I did something like this, negative, let's do this. Negative 5 to 3. Somebody remind me what the square bracket means. Cedric? Yeah, it includes it. Very good. So this would be negative 5 less than x less than or equal to 3. We would show it this way with interval notation. It's a little bit shorter. It's a little bit less writing than that kind of set notation or domain notation. That's what that means. So you got to remember a little bit about intervals of increase and decrease. You got to think about what this end behavior idea is telling you. The fact that it's continuous. This is not supposed to be easy. I am not putting the answers up on the classroom so you can just look at it and say, oh, okay, yeah, now that makes sense. No, the whole point is that you can put the pieces together. You're more than welcome to come and ask me. If it's correct, we'll do it together. But if you get the pieces together, you'll probably be able to convince yourself that it's correct. You're like, yeah, this, once you get there, might take a little bit of struggle. You might have to kind of put some parts together and then erase something and change it. Like that might happen. And if you get 5 of these and not one of them, or if you get 3 or 4 of them and not 1 or 2 of them, I mean, you're at least partway there. You know what I mean? I think B is a little bit tricky to get all of them. It's a lot harder than A. And then there's another one here that revisits some ideas of limits, including with intervals of increase and decrease.